All right, so moving on, we are going to hit upon chapter 4.7, and this is going to be the page that we're working on, and this is all about the multiplication counting principle, factorials, and permutations. So starting out, this is about Dunkin' Donuts. For cold brew, they have three sizes, small, medium, and large, 2 dairy options, cream or none, and 2 sweetener options, sugar or none. Write out all the possible ways to order cold brew. Now, you could reduce, small, medium, and large to S, M, and L, and then cream, no cream, sugar, no sugar. Maybe get those down to all single letters, and you can write them all out in triplets to see how many different combinations you get or different orderings that you get. However, that's kind of problematic because you could miss some. It could easily happen. So one way to avoid missing them is to go ahead and draw what I drew here. I drew it ahead of time so that you wouldn't be bored and waiting on it. But you start out with cold brew, and then I just went in order, and I did like a tree diagram off of that. No probabilities or anything. And I split that into small, medium, and large. And off of those, I went to the next thing, which were dairy options. So cream or none, cream or none, cream or none. And then finally, off of those options, I had the 2 sweetener options, sugar or none. So sugar, none, sugar, none, sugar, none, all the way down. And when you're done, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many ways can you order this? That would be 12 ways. Now this, I spared you watching me do this, which was not what happened in the classroom. They had to sit there and watch me make this tree diagram, and even I was getting annoyed by it. We're going to use this idea called a multiplication counting principle. So we'll start out with 3 sizes, small, medium, and large, so that's 3, and we'll label those sizes. And then 2 dairy options, so 3 times 2 for dairy, and then 2 more times 2 for sweetener. And you can see that if you multiply those, you end up with exactly this. And it's a great rule. It really can spare you a lot of stuff like this, especially if you have a restaurant and the combinations of things that you could make for dinner would be in the thousands. I don't know that you would necessarily want to make that into a tree diagram. It would not be very user-friendly. So for coffee, they have 4 sizes. So I'm just going to start with that. 4 times 7 dairy options, so 7 times 8 flavor options, so 8 times 2 sweetener options. And you would be shocked, this is going to be 448 ways to order coffee. All right? And again, this is going to be our multiplication counting principle, which we will define formally on the next page. And it makes this kind of finding outcomes a lot easier. Okay? So there's not really much more to say about that. So we're going to move on, and we're going to look at factorials next. So at the checkout sign, I guess we're still in Dunkin' Donuts. There is a sign with 2 big promotions. One is to win free coffee for life. And here's how you do it. Using each of the digits 1 through 6 only once, that's important. Create a 6-digit passcode. You then enter your passcode online. If it matches the secret passcode, you win free coffee for life. How many different passcodes are possible? All right. This is going to be a variant of the multiplication counting principle. Right? So if we start out with our first digit, well, there are 6 numbers available for it. So there's 6 possibilities for it. But we have to pick one. And then once it's picked, it's no longer available for any other digits. So the next digit will only have 5 possibilities. And so after we pick one from there, we'll have removed 2 digits from the original 6. Now we're left with 4, and then 3, and then 2, and then 1. And that's going to be, if you pull out your calculator, 720 passcodes. And there's also a name for this sort of multiplication, this sort of multiplication counting principle. These are called factorials. All right, starting with n, which would have been the biggest number, 6, and then just decreasing by 1 for each subsequent digit, and multiplying them together. Okay, and this is shorthand notation is this. 6 with an exclamation point means 6 factorial, and that's what it's read, 6 factorial. Now you do have this symbol, this exclamation point, in the TI-Nspire calculator. I didn't take time to show kids because I don't know that it's really important to find it, but it is there. And if you just type 6 and find that symbol, that exclamation point, and hit enter, you'll get 720. Okay, so the last part of this problem number 3 is to win free coffee for a year. Now they're going to make us make more passcodes, but I'm thinking they won't make us do this many, because winning for your whole life should be a pretty rare outcome, but winning coffee for a year should be a little easier. All right, so we're going to use the same digits 1 through 6 with no repeats. Okay, that's important. We're going to create now a 4-digit passcode, not 6. And we'll enter that, and if we match the secret passcode, we get free coffee for a year. Okay, now how many different passcodes are possible here? Now since it's going to be a little bit different, well, let's just go ahead and do it. For the first digit, we have 6 numbers available, just like before. But we can't repeat that number, so if a 2 comes up, that's going to start our number at 2, or our code, and we can't use it again. So that'll leave us with 5 for the second one, and then 4 for the third one, and then 3 for the fourth one. And then it's got to stop because it's a 4-digit passcode. So if I keep going, it'll be more than 4 digits and it will not match up to the rules of the contest. All right, so this is going to give us 360 passcodes. So it'll be a little bit easier to get the winner. All right, so this is going to be called a permutation. And this will be read 6 permute 4. Okay, and it has a symbol along with it. All right, it's this capital P. All right, 6 is the amount we start with, and 4 is what we want to use. So it's six things taken 4 at a time. Just remember, for permutations, order matters. All right, so if I get the number 2, 3, 4, 5, right, that's my passcode. That is considered different from 5, 4, 3, 2. That's a completely different passcode. Even though the digits are the same, they're just in a different order. So this is how many orderings we can expect to get, which would be 360 different orders of the numbers 1 through 6 picked 4 at a time. Okay? All right, now I'm going to show you the formula, and the 6 is considered N, and the 4 is considered K. So the formula for this is going to be N factorial divided by N minus K, put that in parentheses, and then factorial. Okay? So N here is the biggest number, which is 6. So the numerator is 6 factorial. The denominator is 6 minus 4. So 6 minus 4, but that'll also be a factorial. Okay? So that'll be 6 factorial over 2 factorial, okay? And we can just go ahead and get a number for the numerator, a number for the denominator, divide, and it should be 360. But I'm going to show you that it'll be exactly the same as what we wrote over here. So this is going to be 6 in the numerator times 5 times 4 times 3 times 2 times 1. Got to go from n all the way down to 1. And then for this, 2 factorial will be 2 times 1. And I wrote it way over to the side because that cancels with that. And 6543 is what we have up here, 6543. So that's the formula. I try to avoid the formulas and just, write out how the factorial works until I have to stop it. And I work it that way, okay? So, but it's good to see this formula and see it in action. You never know when you might use it. So scooting to page 2, here are your learning targets, and I've written them all out for you so you didn't have to really sit through me doing it and just watching it. If you need to pause the video, of course, do it so you can copy these down. But just to summarize, use the multiplication counting principle, that's this, to determine the number of ways to complete a process involving several steps. So to find the number of ways to do that, you multiply each number, the number of each option for each step. So like on the front, we had, 3 times 2 times 2, which was 12. So it's like that. And then using factorials to count the number of permutations or whatever, it's just going to have this notation, and it means n times 1 less than n times 2 less than n, all the way down to when you get to 2 times 1, and then the whole thing stops. So here's your example. And then permutations, this is the number of ways to order k items chosen from n total. All right, there is the notation for it. Here's the formula. Although we found that it was pretty easy just to go ahead and, write them out using common sense. So n is the total number of items and k are the number of items that we want. And remember, order matters. So when we do combinations tomorrow, order won't matter. So if I, pick 3 people, 1 for president, 1 for vice president, and 1 for secretary of an organization, Bob, Sue, and Billy would be different if I made it Billy, Sue, and Bob, for the various jobs. But if I'm just picking a team of 3 people, then Billy, Sue, and Bob would be the same as Bob, Sue, and Billy, or any order. But that's combinations, that's for tomorrow. Permutations, the order does matter. So we have to take into account all of the different arrangements. So when you get to a problem and they say, how many ways can you order this, or can you arrange that? Or even if they, talk about how racehorses can finish, okay? One has to finish first, one has to finish second, one has to finish third, one has to finish fourth. And even if it's those same 4 horses winning at different times, that is considered different, okay? So look for that. So here are our apps. We'll get through these pretty quickly. So a local ice cream shop in Dontrell's town is called 21 Choices because they offer 21 different flavors of ice cream. Dontrell likes all but 3 of the flavors that this place offers. He doesn't like bubblegum, he doesn't like butter pecan, and he doesn't like pistachio. So really, when he goes to order, that's not what he's going to be interested in ordering. He's interested in the 18 that he actually likes, okay? So a 21 Choices Basic Sundae comes in 3 sizes, small, medium, or large, and includes 1 flavor of ice cream and 1 of 12 toppings. Dontrell has enough money for a small or a medium, so medium. So cross off the large. He can't afford it. How many different sundaes can Dontrell order that include only the flavors that he likes? Oops, better optimize my PC. Okay, so there are 2 sizes. Really, there's 3, but he can't afford, so he can only pick from 2. There are 18 flavors, so times 18 flavors, because he doesn't like those 3 and he's not going to order them, times the 12 toppings. Now, I don't see any restriction in the problems as it concerns toppings. And you'll notice that this is not factorials, because it's not 18 times 17 times 16 times 14. It's just these kind of random choice amounts. All right. So if we multiply those together, we get 432. So there are 432 possible sundaes. That was quick. Didn't even need all that space. So for number 2, Dontrell could order a cone with 3 scoops of ice cream instead of a sundae. He prefers to have 3 different flavors for variety, and he considers the order of the flavors on his cone to be important. All right, so this has to be orders. This is going to be permutations. Okay. How many 3-scoop cones with 3 different flavors that Dontrell likes are possible at 21 choices? Okay, and give your answer as a number and NPR notation. This is the same as NPK notation. Okay, so remember, there's 3 flavors he won't order. So the most he can order are 18 for the first one. And once he's chosen that, since he's doing 3 different flavors, he has 17 left to pick from. And once he's picked those 2, he's got 16 left to pick from. And that's as far as it goes, because there are 3 scoops in instead of a sundae for a cone. All right? So we'll just call this flavor number 1. Then we'll call this flavor number 2. And this will be flavor number 3. Okay? And that's going to give us, well, we'll do the permutation notation. That's 18 things taken 3 at a time in a permutation where order matters. And that's really it. This times this times this, which is 4,896. Wow, that's a lot. Okay? So there are 4,896 possible 3-scoop cones. 3-scoop cones. And if we wanted to do the formula on this, remember this is n factorial divided by n minus k factorial. All right, that would be n is 18. So 18 factorial. And that's divided by, let's see, 18 minus 3 factorial. That'll be 18 factorial over 15 factorial. And let me show you how easy this is. This is going to be 18, let's put an equal sign here, times 17 times 16 times 15. And I'm just going to stop it here and make that a factorial, because that means it keeps going. It's just going to save me time from having to write all those down from 14 to 1. And this will be over 15 factorial. So cancel, cancel, and this is the same thing as that. See that? So everything works. So there's the easy way. This is the way I would suggest you do it. Here's the harder way, which after a little bit of practice won't be that hard. But in any event, those are the notes for today. So thanks again for watching, and we'll see you for the last one for Chapter 4.